Okay, some terminology before we go into the modeling. Okay, so when we call a series as white noise, okay, so when we say series, it's just a series of numbers. Okay, so series is nothing but a series of numbers. A stock price of Tata Motors. Okay, stock price of Tata Motors, say it is 100 rupees in day 1, 120 rupees in day 2, 125 day 3, 119 day 4. So this is known as a series. Okay, so where it says it's a series of numbers with a fixed interval, right? So when we call a series as white noise, so this is the definition. A series is called white noise if it is purely random in nature. So let epsilon t denote such a time series where it has zero mean and has a constant variance. So zero mean, that means it is like this. It is 50% up positive, 50% negative. So when you sum it, it actually zero. So if you take the expectation of the this term epsilon t, it's actually zero. So in white noise, the mean is zero and the variance is constant. Mean is zero and variance is constant, right? Or we can also say mean is also constant. That's also one form of white noise. Sorry, in white noise mean has to be zero. Sorry. So in white noise mean should be zero and uh, variance should be constant. So in this case, the scatter plot, if you do a scatter plot of that, you will won't find any pattern in the data. Hence, if a data shows a time series shows time series data shows white noise features, so it's considered as a white noise, then you should stop doing time series analysis. Okay, you should stop. There is no point. There is no point doing time series forecasting, because this is one series which cannot be used for forecasting. It's such a random thing. Random series cannot be used for forecasting, right? That's why white noise series cannot be used for forecasting. So you should stop there, right? One of the way to do forecasting white noise is simply take the average. Simply take the average, and that's the best forecast. That's the best forecast available for this series. So simply take the average of the series, and that's the best forecast you can give for the next period. So if series is not white noise, then you can go for time series modeling. And then what are the models available? So we'll start with autoregressive models. Autoregressive models are the models where the forecasting is done based on the past values. So if yt is one is the current value, yt minus 1, yt minus 2, yt minus 3, these are past values. So yt is a function of the different past values, yt minus 1, 2, 2, yt minus 3, and so on, and the error term. But now question is how many past value to use, right? That's the main important thing. How many past value? That means will you take only yt minus 1? Will you also take yt minus 2? Well, we'll see how we determine that, right? The common representation or the model which is represented normally, and we call it the autoregressive model. Autoregressive or the AR model is always with a parameter, right? So when we say ARP model, that means there are p parameters, right? P number of parameters. If you have only this one, all these things are zero, then this is a AR0 model. Okay, AR0 model is yt is equal to beta naught, no y, right? If you have only yt minus 1, then this is a AR1 model. AR1 model. If it is AR2, then up to this much, right? Yt minus 1, yt minus 2. If it is AR3, then include this one also. If it's AR4, go next, and so on. Most of the times you will stop at AR3 and 4. You won't go beyond that, right? Because it will be like I mean, intuitively, you see, today's stock price is related to yesterday's stock price and day before yesterday. But before that, it's a long time. That's a long gap. So we don't take after few series. And we'll see how to determine this actual p-value. What is the best p-value for forecasting, right? So how many number of past values you need to take, that we'll see. Next type of models are known as the moving average model. The moving average models are the one where you forecast by taking the error terms. So if you do a regression of yt with yt minus 1, right, with say beta 1 plus beta naught, you'll get error 1, right? You'll get an error 1. Similarly, if you do yt minus 1 with yt minus 2 plus beta naught dash, you will get error term 2. So in every regression, if you regress uh, the series with its immediate past series, then you will get a error term, right? Epsilon 1, epsilon 2, up to epsilon n, right? Now, instead of using past value, you can actually use this error term for forecasting. Right? This was one of the proposal, that instead of using the past values like white in the AR case, in the moving average case, you use only the error terms for forecasting, right? The representation is same, just that we have replaced the error terms uh, with the so we have replaced the past values of y with the error terms. So we do not have yt minus 1 anymore. Instead, we are using the et and then et minus 1 and so on. And remember that these ETs are assumed to be white noise. That means if you take the mean of epsilon t, it should be 0, and if you take the variance of epsilon t, it should be a constant. So it is 1, or it is a constant value. It doesn't change over time. The next type of models are nothing but they are known as the ARMA models, right? So they have both AR as well as MA representation. That means you use the past values and also the error terms. Okay? So in the representation, you will see you have yt minus 1, yt minus 2, yt minus 3. So you have the past values pretty much like your AR terms. So ARMA, this is called ARMA, right? Auto-regressive moving average. That means you have AR term as well as MA terms. So you have past values yt, yt minus 1, yt minus 2, and so on. And then the error terms also. Epsilon t minus 1, epsilon t minus 2. So it's a combination of both AR plus MA is equal to ARMA. And people have said that this is more accurate many times over AR or MA process. Alright.